Good afternoon, everyone. Today I will talk on mean value theorem, which is subsequence of Rolle's theorem. Okay. So, what is the statement of mean value theorem? Suppose a function is defined on a closed interval x naught y naught, and it satisfies following conditions. First one is f is continuous on x naught y naught. Second one is f is differentiable on x naught y naught open interval. Then there always exists a point z naught in between x naught and y naught such that f y naught minus f x naught upon y naught minus x naught is equal to derivative at z naught. Okay. The meaning of this theorem is that joining the uh, point f y naught and fx naught, you will get a code. That code is parallel to derivative evaluated at z naught. Okay. So so my aim of this theorem my aim of this lecture to tell what are the applications of mean value theorem. Mean value theorem is looks a simple theorem, but in actual it has some application and which help us, okay, to solve some complicated problems and taking decisions. Okay. For example, if I will say that if you have seen maxima and minima in 12th standard, sometimes calculating a maximum minima is not possible where second derivative do not exist, okay, or first derivative do not exist. Okay. Okay, even the function is continuous but it is not possible. So mean value theorem helps in that case. Okay. And it has some other applications also. We can prove some inequalities. Okay. And that help us to solve some problems. Okay. Inequalities are always are backbones of mathematics because they helps to solve the problems. Okay. Proving theorems. Okay. So first applications we are going to discuss finding some important inequalities. Okay. So I am proving a result. Let f be a function satisfying all the conditions of mean value theorem on closed interval x naught y naught. Okay. If derivative of f is bounded, it means the absolute value of f derivative x for all x never exceed k greater than 0, then absolute value of f y naught minus f x naught is dominated by k times of absolute value of y naught minus x naught. Okay. So this is a simple result, we can prove it. Okay. We will apply mean value theorem. Okay. So we just applied mean value theorem. Okay. So there will be z naught in between x naught and y naught. So I can multiply y naught minus x naught both the sides, so I will get this. Okay. Now, and I can take absolute value both the sides, it means I can take mod both the sides. Okay. So I know that derivative is bounded by k, so f dash z naught will be also less than equal to k, so I will put this value. Okay. So k dominates derivative of f. Okay. So I put the value of this and my result is proved. Okay. Now what is the use of this result, why I have proved this result? So I will show that you see the example 1. I will prove this example that sin x minus sin x absolute value is always less than equal to x minus y absolute value. So why I am proving this result? In subsequent lectures we will see uniform continuity. Okay. In uniform continuity we will prove that sin x is a uniformly continuous function. So where I will need this inequality. Okay. So that is why I am proving in this lecture. Okay. Because in subsequent lecture we will going to see uniform continuity of sin x, okay, mod x, all these functions. So in that case this inequality will play important role. Okay. That is why by help of mean value theorem I am proving it. Okay. So this can be proved easily. If you see, I can take fx is equal to sin x. Okay. I have taken fx is equal to sin x. So derivative of f is nothing but cos x, and I know that cos x is always bounded by 1, because cos x minus never exceed minus 1 to 1. Okay, so its absolute value is always less than equal to 1. So I can take my k greater than 0. So derivative of f less than equal to k, the absolute value of derivative is less than equal to k. So I am going to use result 1. Result 1 was this one. So absolute value fx minus fy less than equal to k times x minus y, so that sin x minus sin y is less than equal to k minus less than equal to x minus y. So my result is proved. Okay, I will prove this inequality in subsequent lecture. So that is why I have proved this. Okay, so similarly we can do this exercise, because when I will teach you uniform continuity, i will I will use this inequality to show that cos x sin square x cos square x, these are uniformly continuous functions. So you can try these problems. Okay, so you can try these problems, okay, yourself, so you will get flavor of mean value theorem, okay, of its application. Okay, so now, so what is uh, increasing function, decreasing function, or strictly increasing function, or strictly decreasing function? What are these functions? So we are going to study these functions. Okay, because we are seeing this definition, because we are going to study maxima and minima. So by help of mean value theorem, we will find maxima and minima of some functions. Okay, okay, so for that we need this definition. So when a function will said to be monotonically increasing, you see the part A definition. A function is said to be monotonically increasing or just an increasing function if fx is less than equal to f by for all x such that x is still less than y. It means my function is not going to decrease. If my function is not going to decrease, it means it is going to be monotonically increasing. If my function, second part B, you see that what is strictly increasing function? If fx is less than strictly less than f by for all x y's which are strictly for all x and y such that x is strictly less than y, then f is said to be strictly increasing on I. Okay, what is C? You see what is monotonically decreasing? If my function is not increasing, such function is called monotonically decreasing or just decreasing. So what is the definition? Fx is greater than equal to fy for all xy belongs to I such that x is strictly less than y. Okay, so then f is said to be monotonically decreasing or just decreasing function. So monotonically, so what is strictly decreasing function? You see the part 1, part D. Fx is greater than fy for all xy belongs to I such that x is less than y, then f is said to be strictly decreasing function. Okay, now we are going to see another definition. So what is critical point? Let f be a function defined on x naught y naught and z is point in closed interval x naught y naught. Then z naught is said to be critical point for f if one of the following two conditions hold. Either derivative of f at z naught is 0, or second one is f is not differentiable at z naught. It means derivative of f at z naught is not defined. So what is a critical point? Critical point is that uh, critical, what is the critical point? Critical points means either derivative of function is 0 or derivative is not defined. Okay, such points are called critical points. So when we find maxima and minima, we just find, first we will find critical points, because maxima minima always occurs on critical points. Okay, so that is why we have seen these definitions here. Now, so I have given a note, if z naught is a point of maxima or minima for f, then z naught is a critical point for f. Okay, so see first example. So see first, so we are going to see second application, finding maxima and minima of differentiable function. So this is second application of mean value theorem. Okay, so 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 to see the application of maxima minima by by mean value theorem, just prove second result. Let f be a function satisfying all the conditions of mean value theorem. So f satisfy all the conditions of mean value theorem. So we have four results, which will help to find maxima and minima. First result is, if derivative of function on this interval, open interval x naught y naught, is non-negative, then f is monotonically increasing function on closed interval x naught y naught. Okay, so this is good result. B part, if derivative is strictly greater than 0, then f is strictly increasing on x naught y naught closed interval. Okay, third part, C, if derivative is non-positive on interval x naught y naught, then f is monotonical decreasing function on closed interval x naught y naught. Okay, D part, if derivative is strictly negative, strictly, if derivative of f is strictly less than 0 on close on interval x naught y naught, then f is strictly decreasing function on closed interval x naught y naught. Okay, so we are going to prove this result second. A, B, C, D, all we will prove. Okay, assume that so what was the first part? Derivative is non-negative. We are to show that f is monotonically increasing function. Okay, so f is no derivative of f is non-negative. So we are taking 2 points in open interval x naught y naught such that x is still less than y. Now by mean value theorem, we will get fy minus fx. You multiply y minus x right hand side. So we can write by mean value theorem in this way. Okay, for some z in between x and y. Okay, so since derivative is non-negative, so derivative at z is non-negative, and we know that x is still less than y, so y minus x is greater than 0. So multiplication of f dash z and y minus x will be non-negative. So that is why y minus x is non-negative. So obviously fy is greater than equal to fx. So f is monotonically increasing function. So first part is proved. So B part, if f derivative becomes a strictly greater than 0, so y minus x is already greater than 0, so their product is strictly greater than 0. In that case, fy greater than fx, so f is strictly increasing function on I. So B part is also proved. Okay, now C part, if f dash z less than equal to 0, and we know that y minus x is greater than 0, their product will be less than equal to 0. So in that case, fy is less than equal to fx. So f is monotonically decreasing on I. D part, if f dash less than 0, and we know that y minus x is greater than 0, we conclude that their product is strictly less than 0. In that case, fy is strictly less than fx. So f is strictly decreasing on I. Okay. Now we are going to find, so what is maxima and minima? Okay, what is maxima and minima? Let f be a function defined on closed interval x naught y naught. Okay, so my z naught is belonging in open interval x naught y naught. So first part, we say that when we will say that z is a point of maxima if there exists a naught and b naught such that z naught lies in this interval a naught b naught, and that interval a naught b naught is sub interval of interval x naught y naught. Okay, and on this a naught b naught interval, fx is less than equal to fz naught for all x belongs to interval a naught b naught. Okay, Second, we say that z naught is a point of minima if there exist points a naught b naught with z naught belonging to a naught b naught interval, and this interval is sub interval of the interval x naught y naught, such that fx is greater than f z naught for all x belongs to open interval a naught b naught. In this case we will say z naught is minima, point of minima. Okay, so b, so suppose my z naught becomes x naught, then how we will say that this is point of minima, maxima? Okay, so now we are saying about x naught. We say that x naught is a point of maxima if there exists b naught greater than x naught, such with close x naught open b naught is containing close x naught open y naught interval, such that semi interval, okay, semi close or semi open interval, such that fx is less than fx naught for all x belongs to this semi close interval x naught b naught. Okay, we say that x naught is point of minima if there exists b naught greater than x naught with x naught b naught interval containing x naught y naught, such that fx greater than fx naught for all x belongs to x naught v naught interval. Okay, now suppose z naught becomes y naught, so how to define maxima minima? We say that y naught is a point of maxima if there exists a naught less than y naught with a naught y naught interval containing x naught y naught interval, such that fx is less than fy naught for all x belongs to a naught y naught. Okay, we say that second, when y naught is said to be minima, we say that y naught is a point of minima if there exists a naught less than y naught with a naught y naught contain x naught y naught, such that fx greater than equal to fy naught for all x belongs to a naught y naught. Okay, now we are going to solve to now we are going to find uh, maxima and minima by help of mean value theorem. Okay, so this is the big application. Okay, so we see second example. So suppose we are taking mode function. So we are going to discuss maxima and minima of f. So mode function is defined by minus x if your x is less than 0 and x if x is greater than equal to 0. So we know that mode function is not differentiable at 0. So at 0 mode function is not differentiable. So what was the definition of critical points? A point on which function is not differentiable. So x naught, at x naught it is not differentiable, so x naught is the only critical point. Okay, okay, and we see that derivative of f, wherever derivative exists, it is non-zero. Okay, because I have written derivative at x is minus 1 if your x is less than 0 and 1 if x is greater than 0. So x is equal to 0 is the only critical point. Now you see that derivative of f is less than 0 if your x is less than 0. So we get by mean value theorem. So we if I have told result d, if derivative is strictly less than 0, then function is strictly decreasing on that interval. So f is strictly decreasing on minus infinity to 0 interval. Okay, thus fx is greater than f0 for all x less than 0. Similarly, derivative of f is greater than 0 for all x greater than 0. So by b part, by result second b part, f is strictly increasing on 0 infinity. Okay, okay, so we are going to, so what we got, fx is greater than 0. So you see left side of 0 and right side of 0, the function is 0 value is less than. Okay, so combining both the facts, so f0 is less than fx for all x, it means the point at point 0 function has minimum value. Okay, so x is equal to 0 is point of minimum for function f, and minimum value of f at x is equal to 0 is f0. F evaluated at 0 is 0. Okay, so x is equal to 0 is point of minimum for f, and its functional value at 0 is 0. Okay, now you see the third example. I am taking the question fx is equal to 1 upon 1 plus x squared. Discuss maxima and minima of f. We can do similarly. What is the derivative of f? Minus 2x upon, sorry, there is typo. In denominator it will be 1 plus x square square to the power square. Okay, so derivative of f is equal to minus 2x upon 1 plus x square. Okay, whole square. Then we will put f dash is equal to 0, so we will get x is equal to 0. So x is equal to 0 is only critical point. So derivative of f greater than 0 for all x less than 0, because minus sign is there already in derivative. So we get that f is strictly increasing on minus infinity. So what is the meaning of this? So it means f0 value is greater than fx for all x less than 0. Now similarly, f dash x is less than 0 for all x greater than 0. So we get f is strictly decreasing on open interval 0 to infinity. It means f0 is strictly greater than fx for all x greater than 0. So combining both these inequality, f0 greater than fx when x is less than 0, and f0 greater than fx when x greater than 0. So what we got? We got that f0 is greater than fx for all x. Hence x is equal to 0, point of maximum for function f, and maximum value of f at x is f0, that is 1, because we can calculate maximum value by putting x is equal to 0 in fx is equal to 1 plus x square function. Okay, so now we are going to discuss another question. Question 4 example, let fx is equal to x cube upon 3 minus 3 by 2 x square plus 2x. Discuss maxima and minimum of f. So first you calculate derivative. So we have calculated derivative x square minus 3x plus 2. So it can be factorized x minus 1 x minus 2. So putting the derivative 0, you will get x is equal to 1 and x is equal to, so x is equal to 1 and x is equal to 2 are critical points. So we will check separately at x equal to 1 and x equal to 2. So first check at x equal to 1. Okay, so since derivative, if you will take any value less than 1, so the factor x minus 1 will be strictly negative. Okay, and x minus 2 factor will be strictly negative. So product of two strictly negative values or less than 0 values, their product will be greater than 0, strictly greater than 0. So that is why derivative of f greater than 0 strictly greater than 0 for all x less than 1. So we get f is strictly increasing on interval minus infinity to 1. Okay, so what is the meaning of this? It means f1, because function is increasing, so value f1 will be strictly greater than fx for all x less than 1. Okay, similarly derivative of f still less than 0, because in the interval 1 to 2 the factor x minus 1 will be strictly positive, but x minus 2 factor will be strictly negative, but so their product is strictly less than 0. So derivative is still less than 0. So we get that f is strictly decreasing on 1 2. So what is the meaning of this? It means f1 value is strictly greater than fx for all x in between 1 to 2. So combining both the inequalities, we get f1 is greater than fx for all x by 2. Sorry, f1 is greater than equal to fx for all x less than 2. Hence x is equal to 1 is a point of maxima for the function f, and maximum value of f at x equal to 1, f1 is equal to, that comes to 5 by 6. Okay, now we have calculated maxima minima x equal to 1. It means we have discussed. So we have discussed. So now this x equal to 1 critical points maximum minima is done. Now we are moving to discussing x is equal to 2. Similarly, derivative is when derivative is greater than strictly greater than 0 for all x greater than 2, we get that f is strictly increasing on 2 infinity interval. Okay, thus fx is greater than f2 for all x greater than 2, strictly greater. Okay, we already know that f is strictly decreasing on 1 to open interval. So thus fx is greater than strictly greater than f2 for all. Okay, we already know that f is strictly decreasing uh, on 1 2. Okay, 1 2. So fx is strictly greater than f2 for all x in between 1 and 2. Okay, so we have fx is greater than equal to f2 for all x in between 1 and 2. Hence x is equal to 2 is a point of minima for the function f, and minimum value of f at x is equal to 2 is f2 is equal to 2 by 3. Okay, now we are going to discuss last problem or example of this lecture. Okay, so we are taking function fx is equal to x cube. Discuss maxima and minima of function f. So just you calculated derivative. So derivative is 3x square. So x is equal to 0 is the only critical point, because we can put derivative 0 and x values, after solving x values are going to be 0. Okay. So observe that if my x is not equal to 0, 3x square is still greater than 0. It means fx in the open interval minus infinity to 0 function is increasing. It means in the open interval minus infinity to 0, fx is less than f0 for all x less than 0, and in the open interval 0 to infinity, f0 is still less than fx for all x greater than 0. So if you see, before 0 function is increasing, and after 0 function is also increasing. So what does it mean? It means f is neither maximum nor minimum at x is equal to 0. Okay, hence no maxima or minima points exist for f. So in this lecture it is up to you, sorry, up to this. Okay, up to this. So in this lecture I am summarizing this lecture. What we have discussed in this lecture, we have seen application of mean value theorem of mean value theorem. Okay, so we have studied two application. First application is finding inequalities, important inequality. Second, discussing maxima minima. Why we are discussing discuss maxima minima? Because sometimes, because you have seen maxima minima in 12th standard, where derivative first second third function was differentiable more than one time. Okay, but here if your function is not differentiable more than one time, still you can calculate by mean value theorem. In certain condition it is possible. So that is why it is important. Okay, so thank you very much for today's lecture. Please, you can give any comment on this lecture, or if it's possible for you to subscribe it, is subscribe, you subscribe it if you like it. Okay, it is not that you are forcefully to subscribe it. Okay, so thank you very much. Your comments are welcome. Please comment on this lecture. Okay, okay. We have proved one inequality is for sine functions, so we will use their inequality later. Okay, in subsequent lecture. Thank you very much. Please like, comment and subscribe the channel. Thank you very much.